All right. Okay. Hi, everyone. Thank you for joining. Can everybody hear me okay? Just someone wave or something like that. All right. Okay, great. We have 3 wavy people and a few black squares. Great. Okay. So today we'll be continuing what we did last time. So we'll be finishing up our what we were doing, our intro to quantum information. We left off with Deutsche Algorithm, so we're going to finish up. We're going to be finishing that up. And then we're going to be talking about slightly more realistic systems, still within quantum information. We're going to be talking about the density matrix, and then we're going to be talking about measurements a little bit. And then once we're done with measurements, we're going to be going on to our next part in this course, and we're going to start talking about spins, magnetic moments, and so on, and move slowly into NMR. Okay, so that's kind of where we're going right now. So let me just finish off the Deutsch algorithm, and then we'll be able to continue. Before I do that, are there any questions regarding last lecture, things that were unclear, needs clarification, you had a week to think about it, things like that? Okay, if not, I will continue. Just a second. Okay, all right. So we left off last time with just showing an example of the simplest algorithm, Deutsch's algorithm. Okay. And the idea of this algorithm is pretty simple. It's a one-bit algorithm. And the idea is that we want to know if the function f of 0 equals f of 1, or if f of 0 does not equal f of 1. Okay, so f is a one-bit function. It gets 1 bit, and it outputs 1 bit. Okay, so it could be that f of 0 equals 0 and f of 1 equals 0, and that's this case, or equals 1, or f of 0 equals 0 and f of 1 equals 1, and they don't equal, and so on. So there are basically four options for this function. And we wrote the circuit. So the circuit starts with two qubits, which are initialized to 0. So this is the initial state. Okay, we call this psi naught, 0, 0. Then we apply a Hadamard on qubit number 1, and we apply a NOT operation and then a Hadamard on the second qubit. Okay, and then we're going to be in psi 1. Okay, so I'm writing the circuit, and then we're going to calculate at each step what is the wave function of the system. Okay, now after that occurs the main calculation. Okay, u of f. So this is a unitary operation, and what this unitary operation does, it gets an input of x and y, and the output is x and y plus f of x. Okay, where this plus here is a bitwise addition. Okay, it's a bitwise addition.
Hi.
Yes.
It's a bitwise addition modulo 2, right?
Yeah. So yeah, if 0 plus 0 will be 0, 0 plus 1 will be 1, 1 plus 1 will be 0.
But 1 plus 1 will be 0.
1 plus 1 will be 0, yes.
Okay, thank you.
Yeah. Okay, so then we will get here. This will be psi 2. Okay, and then we have one final operation, Hadamard, and this will be our final state, psi 3. Okay. Now note that we don't know what f of x is, But whatever f of x is, we can construct it. Okay, so suppose that, let's pick on someone, Amot. Okay, so he has f of x and he constructs this function. Okay, so if f of x, for example, let's suppose that f of 0 equals f of 1 equals 0, then Amot has no work and he just has nothing, puts here nothing. Okay, or for example, if Amot decides that f of x, f of 0 equals 0 and f of 1 equals 1, then he would put a not operation here, okay, between these two. But let's say Noah, she doesn't know what u of f is, okay? And Noah wants to know what f of x is, and if this was a regular computation, she would need 2 calls of this u of f, okay, in order to figure out if f of 0 equals f of 1, or f of 0 does not equal f of 1. Okay, and what we're going to show here is that with 1 call of this u of f, meaning with this circuit, we can figure out, are we in this case or that case? Does that clear up the problem? Yeah? All right, there are 2 nods. 2 nods is good enough. Okay, all right, so we started here, and let's write psi 1. So after a Hadamard and an x Hadamard, we're left with 1 over square root of 2, 0 plus 1, 1 over square root of 2, 0, minus 1. Okay, so this is the Hadamard and this is the x Hadamard. Okay. So we're over here. And now we're applying u of f. Okay, so now we're applying u of f onto psi 1. Okay. And that will give us the following state. X, 1 over square root of 2, 0 plus f of x minus 1 plus f of x. Okay? So this is applying u onto psi 1. You can also write this in this way, minus 1 to the power of f of x over x, 1 over square root of 2, 0 minus 1. Okay? That is another convenient way of writing it.
Question?
Yes?
Shouldn't there be a summation over x?
Yeah, so it depends what x is. So if x, so x, it can be superposition. Here you're going to see that x is coming in as a superposition. So when you plug into this, and I'll do it explicitly in the next line, but when you plug into this, then you're going to have, 0, and if whatever f of 0 is, okay, 0, whatever f of 0 is, that will give us the sign, times this, plus 1 minus 1 to the power of f of 1, okay, times this part, okay? So you need to plug it in, but if x is 0, then it's trivial, then simple. If x is superposition, then you got to plug in the superposition. So 0 plus the 1 part, okay? All right, so was that a question? No, okay. So I'm going to write, so what I explained to you now in words, I'm going to write explicitly, okay? I'm going to move to the next board here, okay? So this is psi 2, okay? So you could do an equal sign on the previous board, but this is psi 2, okay? Maybe I'll move psi over here. So psi 2. And to make it simple and explicit, we're going to divide psi 2 into 2 cases. One case where f of 0 equals f of 1, okay? And in that case, if we plug in to what we wrote, just like I explained a second ago, then we will get plus or minus depending if f of 0 equals f of 1 equals 0, or f of 0 equals f of 1 equals 1. So the plus would correspond to the 0, the minus would equal to the 1. And then you will get 1 over square root of 2, 0 plus 1, 1 over square root of 2, 0, minus 1. Okay. Now, for the case where f of 0 does not equal f of 1, then you would get plus minus 1 over square root of 2, 0 minus 1, 1 over square root of 2, 0 minus 1. Okay? And this is exactly doing what I just explained. So on the previous term where we saw x, we're plugging in, because x was 0 plus 1, so we plug it in with 0, and then we plug it in with 1, and we do the summation. Okay? And now we do the last step of the circuit that's on the other board. I remind you that's just doing a Hadamard on the first qubit, which gives us psi 3. Okay? And then psi 3 is just going to be, for the first case, where f of 0 equals f of 1, it's going to be plus minus 0, because 0 plus 1 goes to 0 under Hadamard. 1 over square root of 2, 0 minus 1. And for the case of f of 0 does not equal f of 1, then we get plus minus 1. Same thing. 1 over square root of 2, 0 minus 1. Okay? And now the situation is pretty clear. Okay? Because you can measure the first qubit. Okay? And if the first qubit gives us 0, then we know we're in this situation. And if the first 0 gives us 1, we know that we're in this situation. Okay? A shorthand for writing this is just saying that our state here just equals f of 0 bitwise f of 1, okay, times 1 over square root of 2, 0 minus 1. Okay? So with one call of this function, we're able to infer this global property of the function. Okay? So just to be explicit, we measure Q1 to get f of 0 plus f of 1. Okay? And this is really a simplest example you can give to show how you can get a global property of a function using entanglement. Okay. Are there any questions about this? Was everybody able to follow? Yes? No? All right. Okay. No unhappy faces. Great. So with that, I'd like to move to the last part of this quantum information intro and start talking about a bit more realistic stuff. Okay. So when we're talking about real life, okay, and we talk about quantum mechanics in real life, then we're talking about basically statistical ensembles. Okay, in real life, when we deal with qubits, we're dealing with qubits which are not pure. Okay, we're dealing with qubits that are not pure, basically because we're dealing with ensembles. Okay, quantum mechanics really deals with statistics. Okay, you can maybe I'll write it explicitly here. Quantum mechanics, right? The predictions, maybe. The predictions of quantum mechanics are statistical only. Okay? We can take a single qubit and we can measure it and get a single result, but really that's insignificant. Okay? Where quantum mechanics comes in, okay, is by predicting the statistics of the outcomes. Okay? And since the measurements themselves are probabilistic, then you have to deal with statistics. Okay? This means that we need to be able to describe ensembles. Okay? We need to be able to describe ensembles of quantum states. And a very good way of doing it, or formalism, a very convenient formalism to do that, is using the density matrix. Or sometimes referred to as the density operator. Okay? Now, do like a red X on your thing if you've never heard of the density matrix, just so I know if there is anyone who has never heard of it. Okay, no red X's. Great. Okay. So, density matrix. Okay. Sorry. Rho is defined as the sum pi psi I psi I. Okay. Now for a pure qubit, okay, so a single qubit, okay, which is just psi alpha 0 plus beta 1, okay, then the density matrix is just going to be psi, which is just alpha squared, beta squared, alpha beta, and I don't want to get the stars wrong here, like that. Okay? And if you want to parameterize it like we did on the block sphere, then it will be like I basically plus sigma x, your Pauli operator, sine x, sine phi, cosine phi, plus sigma y, sine theta, sine phi, plus sigma z, cosine phi, cosine theta, sorry.
Shay, shouldn't there be only one star on each of diagonal element?
Yeah. Hang on. Yeah.
And on the alpha?
Yeah. Like that.
Thank you.
Okay. All right. So, yeah. Okay, so an ensemble of qubits. So if we have an ensemble of qubits, okay, or what we would like to call an unpure qubit. Okay, so now each qubit is in a different state. Then the density matrix can be just written like this. So it's half I. I is the identity. I didn't mention it here. Plus sigma x, the average of x, sigma y, the average of y, plus sigma z, the average of z. Okay? And the way you want to think about a density matrix, okay, it's a big matrix, okay, and it will always have some diagonal elements. Now these diagonal elements are, anyone?
Eigenvalues.
Yeah, they give us the populations, okay? They give us the populations of the different states in the specific basis. Okay, so for a qubit, you can see here this is alpha squared and beta squared. The probability to be in the ground, probability to be in excited. Okay, so the diagonals will always be the populations. Okay, and the off diagonal terms. Okay, so the off diagonal terms are the coherences. Okay? So if you have a density matrix with basically only a diagonal and off and zeros on the off diagonal, okay, it means it's a completely classical mixture. Okay? There are no coherences between any of the constituents. Okay? On the other hand, anything off diagonal will mean that there is some coherence. So a simplest example, again, is a single qubit. Okay? If you're describing, a statistical ensemble of two qubits, one of them is in 0, the other one is in the 1 state, you would get a density matrix with a 2 by 2 density matrix with an element here and an element here, telling you what is the probability of this qubit and probability of that qubit. And on the other hand, if you have a qubit which is in a superposition, 0 plus 1, then your density matrix will look like we'll just have 1, 1, 1, and 1 with a half prefactor. Okay, so you will have off diagonal elements. Okay, so that's the simplest example. Okay. Now let's move to the other board and write a few more properties about the density matrix, and then we can talk a little bit about measurements. Okay, so some properties, some properties that I would like to remind you of. The first one is that the density matrix transforms like an operator. Okay. This is why it's referred to as the density operator. Okay. It means that if I have some psi and it transforms under some unitary u into u psi, okay, then rho under the same unitary will just transform as u rho u dag. Okay. The second property really comes from when we were talking about the diagonal part. It says that the trace of rho is just some I pi has to equal what? Anyone?
1.
1. All right. All right. Is that the same person answering every time? I don't hear a yes. All right. Okay. All right. Yeah, all your voices sound the same on the Zoom, so it's a little hard. Okay. Okay. The third property regards the purity of the state. Okay, so if we do a trace of rho squared, okay, then we know it has to be equal or smaller than 1. And if trace of rho squared equals 1, okay, it necessarily means that rho is pure. Okay, which means that we can write rho as some psi. And also the reverse. If rho is pure, which means you can write it as psi, then the density matrix, then the trace of the square of the density matrix will equal 1. Okay. The fourth thing I want to talk about is maybe a property that you don't know about, and this is called purification. Does anyone know what purification is? Ever heard of it? Heard of that property? Anyone? No. Okay. All right. Well, purification basically means that any density matrix is a pure state on a larger Hilbert space. Okay? Was anyone familiar with this? If anyone is familiar with this, put like a green little tick thing. Yeah, we have a nice percentage of green tick things. All right, 3 people. Excellent. Okay, so what I'm going to do with this, I'm going to first show you the proof of this thing, and then I'm going to discuss the consequences. Okay? All right, so on the next board, I'm going to show you the proof. And I'm going to show you the proof basically because it's a 2-line proof, so it's easy to prove it. The second reason I'm going to show you this is that it allows me to introduce a partial trace, which I guess, I don't know, some of you don't know what a partial trace is. I assume most of you do, but some of you maybe don't. It allows me to introduce that. And it's important for measurements, okay? Because when we actually do a measurement in reality, what we're doing is we're doing a partial trace, okay, on our Hilbert space, and we're left with our system. Okay? We're going to discuss this a little bit more. Okay? So this is important for that. So remember, this purification thing just means that any density matrix is actually a pure wave function on a larger Hilbert space. So let's prove that, and then I'll let you ask a few questions about this. So I'm moving to the next board here, and here we're going to write the proof. So we're going to take rho A, and rho A is just sum over I pi psi I over A psi I, okay, where psi I, okay, are states that belong to Hilbert space A. Okay, so we have our small Hilbert space A. We have our density matrix over this Hilbert space. Okay, and what we want to show is that we can always find some phi AB, okay, some wave function phi over the Hilbert space AB. So phi AB lives in the space of A and B, okay? Such that the partial trace, so rho A, will equal the partial trace over B of phi AB. Okay, so we have the density matrix, our pure density matrix, phi AB, and we want to do a partial trace over B, such that we're left with rho A, this thing. Okay, and now I'll write here the definition of a partial trace. Okay. So trace B of sum rho AB equals sum over ij kl. Those are 4 indices. Then we're going to have c ij kl. Those are just the coefficients, the numbers in the matrix itself. Okay. ai, aj, bl, bk. Okay. Where ai and bi, okay, these are basis states for HA and HB. so this
Shouldn't
is the partial trace.
be in an
Yes.
Shouldn't the B's be also in an auto product?
No, we're tracing out. Okay, at the end we're going to be
This
left
is
with.
after applying the trace.
We're going to be left with two indices at the end. Okay, we're going to be
Okay.
left with
Thank you.
I, J indices. We're tracing out, we're summing out the K and L indices. Okay? If you think of two matrices, think about how you get, you take one Hilbert space and another one, okay? And you do a product between them, you get this one bigger matrix, right? Okay? So think about the original indices of A as IJ and the original indices of B, and now you're just contracting it back. Okay? But now you're summing over them. Okay? All right. But, you know, as you look at that, you can already see that this is basically the proof. Well, I'll write it here explicitly. Okay? Basically, if we define phi A, phi AB to be sum over I square root of pi psi A phi I of B. If you take that and you plug it in to this equation, then you just get this. Okay? Now there is an assumption here. Okay? The assumption is that the dimensions of HB, okay, are larger or equal to the dimensions of Hilbert space A. Okay? It just, because you need enough coefficients here, you need to be able to sum enough coefficients to get the full density matrix. Okay? So when you're purifying, your new pure state has to be on the Hilbert space, which is at least as large as the sum of your original one plus an additional one. Okay? An additional property that you can see here also is that this decomposition is not unique. Okay, so if you think about an ensemble of qubits, go back to the simple example of a qubit. You have one qubit. This qubit, this density matrix, let's think of a density matrix with only two diagonal elements for an ensemble of qubits. So you can have many qubits that are zeros and many qubits that are 1, and that will give you a density matrix. You can have many qubits that are in the plus state and another same number of qubits that are in the minus state. That will give you the same density matrix. Okay? You can have a bunch of qubits that are randomly distributed around the Bloch sphere, completely random, and that will give you the exact same density matrix. Okay? And the main point is here that you really cannot distinguish between those states. Okay? Once you have a density matrix, if all you have access to is that density matrix, then you cannot tell what is that density matrix composed of. Okay? What ensembles is it composed of? Are all my qubits in there 0, 0, 0, 0 and 1, 1, 1, 1, or are all of the qubits there minus, minus, minus and plus, 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 plus? Or another interesting example is maybe take a 2-qubit example. Okay, here's maybe a 2-qubit example. So a 2-qubit example, like I said, you can have one qubit which is in 0 and another qubit which is in 1. That will give us a density matrix with diagonal elements here and here. Okay? 1 and 1. Half and half. Half and half. But also, what happens if we purify this? We can purify it any way we want. We can also purify this into a Bell state, for example. So take a Bell state, 0, 0, plus 1, 1. Okay? Yeah. Never mind the normalization. Doesn't matter. Take this Bell state. Do a partial trace on the Bell state. What do we get? Anyone? No one's listening? Everyone's microphones are broken.
The same one?
We get the same thing. Half and half. Okay? I'm tracing out, I'm just looking at one qubit. And that qubit looks like a completely mixed state. Okay? But on a larger Hilbert space, it's actually a Bell state. Okay? But if I only have access to that single qubit, think of Alice and Bob. If Alice only has access to her qubit, and she cannot communicate with Bob, and all her experiments are only on her qubit, and all information is from her qubit only, there is no difference between a completely mixed qubit and the fact that she had a Bell state. It forms no resource. Okay? You can expand this towards more philosophical discussions, like, if you look at this thing, then you can say, okay, any state that I have, I'm just looking at part of the world, and the world is really a big wave function that just moves on in a unitary way. And all I'm doing is, I can't keep track of all those degrees of freedom. And thus I'm tracing out part of the world in order to be able to handle my experiments, the real world that I see around me. But really there's this one big evolving wave function. And this kind of fits with the philosophical notions of many worlds. Okay? Or you can say, somebody actually measures those things and there's collapse over there and you're left with this density matrix. But the main point is that for you as an experimenter, for you who only has access to this density matrix and don't have access to the rest of the world, to the part which you traced out, the predictions of quantum mechanics are not going to change. They're going to be exactly the same. Okay? Any questions about this? Is that clear? Interesting at least? No? Nothing? All right. I can't see smiles on the Zoom. Okay. So before we move on to measurements, I want to write down, just to make sure that everybody remembers, two more properties of the density matrix, and then we'll discuss measurements. Okay? So, the Schrodinger equation for the density matrix, so written in terms of the density matrix, the Schrodinger equation just reads as rho dot equals minus I over h bar, commutator of h rho. Okay? And the average of some operator A equals the trace of A rho. Okay? I'm just writing it down to remind anyone who's forgotten this. Okay? And we'll move on to talking about measurements and how measurements are defined. And while I'm erasing the board, it's a good time to ask questions. Preferably physics related.
I have one.
Yeah, physics related?
Yes.
Oh, then you can't ask.
Can you explain the idea again of the purification?
Yes. Well, I erased the board, but maybe I'll go to this board here in the proof. Okay. So who was that asked?
Amot.
Amot. Hi, Amot. So the idea of the purification is, remember, you have your density matrix, you have your small Hilbert space HA. Okay? What the purification says is that you will always be able to find a larger Hilbert space, okay, which is decomposed. Here I've just defined it as HA Kronecker product with HB. Okay, so this is a larger Hilbert space. HB has to be at least of the size of HA. Okay, so now you're looking at your bigger Hilbert space. You will always be able to find a pure wave function. Okay? A pure wave function, it means that your density matrix will be able to be represented as phi AB phi AB, okay? So if you take your whole Hilbert space and you calculate the trace of rho squared, it will be 1, okay? So a pure wave function, you will always be able to find some pure wave function like that, okay? That's the idea of the purification, or what the purification means in that context, okay? So even if you have a completely mixed state, okay, so a completely mixed state, right, would be, for example, an ensemble of qubits which are randomly distributed, okay? On a large enough Hilbert space, they will form a pure wave function, okay? And what I tried showing is the nicest example, the nicest, simplest example of really the Bell state. Okay, because you think about a Bell state, this is a nice entangled state with the largest correlations you have. But if you're just looking at your small qubit, if you have a completely mixed qubit, half and half, okay, that looks really like, you know, it's a classical thing that it has a probability to be in 0 and a 50% probability to be in 1. And that's if I'm only looking at this qubit. But actually, it can be described on a larger Hilbert space as a Bell state. It doesn't really help me in any resourceful way, okay? And this is why I said, you know, it goes a little bit to philosophical discussions. Is the world a big wave function and I'm just looking at one small part of Hilbert space where I traced everything out, or is there some collapse going on? That's more philosophical. But at the end of the day, you have your density matrix, okay? And it is just very convenient to be able to deal with a smaller Hilbert space and trace out and not worry about what's going on in these degrees of freedom which I cannot access. Okay, the main point is I really cannot access those degrees of freedom, or it is hard for me to keep track of everything that's going on. And I can't deal with such a large Hilbert space. Okay? So you can trace out everything and just deal with your little system that you're worried about, and you can track what's going on about that. And because you can't track all those degrees of freedom, then that is kind of what a measurement is at the end of the day. Okay? A measurement is the information goes somewhere to a larger Hilbert space, and we can't really keep track of it, and we don't know what's going on, so we're doing some statistical summation over it. Okay? That's kind of the notion that I want to explain. Okay? But it really, it's you at the end you only want to deal with this density matrix that you have, and if you only have access to that, then it doesn't really matter. Okay? Or it matters because there are measurements, but yeah. Okay.
But what happens if HA is not finite Hilbert space, or maybe not even a countable Hilbert space?
Oh, if HA is not finite?
Yeah, not even a countable, like we have in quantum mechanics for the momentum space.
Yeah, so for position, so yeah, so good, that's a good question. So if you'd have position and momentum, okay, then you're asking a good question. Can I always find, can I always purify it? I think you can always somehow at the end, maybe you can cut your Hilbert space, make it finite somehow, say, okay, I only have access to this much momentum in this much space. But you're asking a question that I don't have a good answer for. Okay, I know that this works for finite. I don't know if you can always purify for a non-finite Hilbert space, because then I don't know what that would say about HB.
Okay.
Okay,
Thanks.
I can get back to you and answer that question. It's a good question. I don't know.
Thanks.
Any other questions? Okay, good. All right. So let's move on with measurements. Okay, so quantum measurement. I'm still following Nielsen and Chuang here, but I'm taking some of the stuff is taken from this book by Wiseman and Milburn. It's called Quantum Measurement and Control. Chapter 1. I took some stuff from chapter 1 there. It's a fantastic book, by the way. Very recommended reading at least the first 2 or 3 chapters. Very insightful. Okay. So quantum measurement, I assume, you know, you've all taken a quantum class and you've all seen measurements and you've all seen projective measurements. And I think some of you may have seen the more general definition of a measurement, which basically means that we have some set of m. Okay, so you have these operators m. These are operators. Okay, so I'm going to give the general definition of a measurement, and then I will show you how projective measurements are a subset of this. Okay, and then I'll also introduce what POVMs are, which some of you may not, some of you may. Okay, and explain where they come into the context and why they're important. Okay, so we're starting with the general definition of a measurement, and that is basically a set of some operators m, where the probability of getting some m, outcome m, so small m is the outcome of the measurement, and large m is the operator. Okay, so the probability to get some outcome, so this is an outcome. Okay, it can be a number or whatever, is just psi m dagger m psi. Okay, m. Or in density matrix form, m dagger m rho. Okay. The post measurement state so what happens to the system after the measurement is given by psi m, so this will be after the measurement. This is our operator, psi square root psi m dagger m. This is just the normalization psi. Okay, or in density matrix form, rho m, meaning rho after the measurement. Maybe we'll change this to rho f, final, psi final. I don't know. Less confusing. It will be mm rho mm dagger over trace. Same thing. Mm dagger mm rho. Okay. And because this is a measurement, we require what is called the completeness condition. And this is the sum over m dagger mm has to equal 1. Okay? Or in other words, the sum I over pi, the probabilities over here have to equal 1. Okay, so this is the most general definition of a quantum measurement, and all that we require is that the sum of the probabilities sum up to 1. Okay? Now, what is typically more familiar to you is, for example, for a qubit, you would define, M0 to be, let's say, 0, and then M1 to be 1. This would be for qubit. For qubit in the computational basis, you would define this thing, and these would be the projectors. And a lot of the time you hear the two words, these M operators have to be Hermitian. Anyone heard that? Anyone heard that claim? Oh, or my measurement operator has to be Hermitian. Well, that is true for projective measurements. Was that a question? Or is this someone saying, yes, I heard that it has to be Hermitian?
Just answering your, I said yes.
Okay, yeah. So for projective measurements, and this is what you usually learn about, okay, so this is, let's call this the usual case. Our operators are Hermitian, okay? The are Hermitian, okay? Or in other words, they're orthogonal, and which means that M prime will equal delta M prime M. Okay, but that is not necessary. Okay, that is not necessary to happen. Now, but for projective measurements, they're very nice. Okay, they're the common type. They're what you learn at the beginning, and I'm sure that you were introduced with projective measurements at some point, and the whole concept was very confusing. Did anyone accept the concept of projection of, oh, you measure and suddenly your state is that? Was anyone very happy with that, or was everyone like, what? What's going on? There's some instantaneous something happening, okay? There's some problem with something instantaneous happening, really, in this life. Nothing happens instantaneous. But the whole thing is very confusing that we just move along and say, okay, there's these projection measurements, and it's just a mathematical operator, and it's an abstraction of something, and we move on. Okay, and we forget to ask ourselves many other things. And then we start learning about them, and we know about all their nice properties. Okay, and projections have really nice properties. Okay, the final state, for example, once we measure, we know the final state, and the final state, the final state of our system has projected. This is why it's called a projection, onto one eigenstate of our basis. Right, we have an operator. We have our eigenstates, we get some eigenvalue, and after the projection, we've projected into that eigenstate. Okay? Now what happens if we do another projection on the system? What do we get? The same result. Okay? And we can keep doing the projection over and over and over and over again, and we keep getting the same result. Okay? It's what is called a QND measurement, quantum non-demolition measurement. Okay? This is not, it doesn't have to be the case, okay? If you consider, I had something written here as an example, a photon counter example, okay? So if you have a photon counter, you've probably been in a lecture where someone drew something and then says, okay, here's a photon counter, and the photon comes along and it counts the photon. That measurement, you cannot repeat the measurement on the photon is gone, okay? All right. So in that sense, it's not a projective measurement the way you learned it. Okay, it's a demolition measurement. So when we talk about projective measurement, it's a projective measurement. It's a measurement that leaves your state in the eigenstate of that system. So it's very convenient because you can do these repeated measurements, and they're QND, and your state collapses, and it has these nice properties. Okay, but you don't have to do that. Okay. As long as long as the sum over m dagger m equals 1, okay, then you have a measurement. Okay, and in the more general sense, what people usually do is you construct a set of operators, okay, which are called POVMs. So a measurement can be constructed from the set of EM. Okay. I think this notation is also from Nielsen and Chuang, so if you're looking for this, that's the book. Where EM is defined as m dagger m. Okay, and the set of okay, the set of EM is called a POVM. POVM stands for positive operator valued measure. Okay? And it is sometimes a lot more convenient to use POVMs. When it's first introduced mathematically like this, it's a little confusing as to why do we actually need this. We have projections. It also gets very confusing when you realize the following fact that any POVM can be represented or can be decomposed, okay, into a unitary plus a projector. So your measurement, okay, can be decomposed into some unitary over here, followed by, a projector. And then you're thinking, okay, you have these general measurements. We learned about projections. Now you're telling me projections are not important. Projections are not the big deal. They're not the main thing. There is a more generalized thing, but this generalized thing can be decomposed into a unitary plus projector. Then why do I need this thing? What's the point of this? And to give you an intuition as to where POVMs come in, they come in when we're talking about real measurements. And when we want to talk about statistical ensembles, and sometimes when we want to talk about the outcomes of experiments, but we don't care about the post-measurement state. Okay? Maybe in a more intuitive sense, you can think of a POVM. A POVM basically to a projection is a little bit like what the density matrix is to the wave function. Okay, so we had the purification, if you remember before. You have your big Hilbert space, and you trace out part of it, and you have your density matrix, and it describes the world that you can keep track of, take care of, look at. Okay, and you're tracing out this thing. Okay, in a sense, a POVM does the same thing for projectors. Okay, so I can describe everything with pure wave functions, unitaries, and projectors, and that's great. But a lot of the time, it is more convenient to use density matrices and to use POVMs, more generalized measurements. Okay, so this is kind of like the concept. So when you're using tools like the master equation or the stochastic master equation to solve dynamics of a system, it is very convenient to infer from those equations, for example, the POVM, and know what is the effect on the dynamics and things like that. Okay, but just not to leave you empty, I want to show you a simple example of a POVM. This is also taken from Nielsen and Chuang. then I'll say something about continuous measurements, and then we'll take a break. A 10-minute break. Okay, so this is a Povm example. It's taken from page 90 in Nielsen and Chuang book. Okay, I keep repeating the books that I take these from in hope that you open these books. Okay, and so the example goes like this. What we're going to do is we're going to define a Povm that's going to be helpful in a very specific situation. And the situation includes two people. Who are those two people?
Alice and Bob.
And now we'll have Elad and Aviad, because those are two names that I can see on my screen, and they're black squares. Okay. Hi, Elad. Hi, Aviad.
Hi.
Hi. Great. Excellent. Okay.
Hi.
So we have Elad and Aviad. Very confusing. Both of them start with Aleph. There's also Alina. That's also very confusing. Everyone starts with Aleph. We'll have to go back to Noga. I don't know what, but you know, at least she doesn't start with an Aleph. Anyway, the idea is this. Aviad sends Elad a qubit. Okay. And this qubit is in one of two states. It is either in 0 or that state is in 0 plus 1. Okay? And Elad wants to distinguish one of those two states. Now, 0 and 0 plus 1 are not orthogonal to each other. So there is no measurement in the world that can perfectly distinguish between them. Okay? In a single shot, in a single projection, you cannot distinguish perfectly between 0 and 0 plus 1. Okay? But we can construct a measurement that will do a relatively good job of it. Okay, so we're going to construct a Povm, and this Povm will never get it wrong, and when it gets it right, it will have the right answer. Okay, so let me write it down, the Povm. So we're going to construct the Povm. E1 is going to be square root of 2 over 1 plus square root of 2, 1. You can ignore the normalization factors, they're not that interesting. E2 is going to be 1 over square root of 2, 1 plus square root of 2. 0 minus 1 over square root of 2. 0 minus 1 over square root of 2. Okay, this is E2. And E3, since we need all the E's to sum up to 1, E3 is just going to be 1 minus E2 minus E1, E3. Okay. So this forms a Povm basically because E3 plus E1 plus E2 equals 1.
It's E1 in the last, in the E3 it's 1 minus E2 and E1, right?
This is 1. Yeah.
And the last one, it's E1, right?
This is, sorry?
1 minus E2 minus E1.
Oh, sorry. Yes,
Okay,
yes. Sorry. Yeah, so then they all sum up to 1. Okay. And it's easy to see what happens. Suppose that Aviad sends Elad a 0. What happens? Aviad applies this measurement, this Povm, and Elad will never get the result 1. Okay? Aviad will either get 2 or he will get 3. Okay? Okay. And also...
and again, I try to understand what you meant by it.
I meant that if if you send the state 0, okay, you will never
Okay.
get the result 1.
Okay.
Do you agree with me? Do you agree with me?
Yes.
Okay, good. If I send the state 0 plus 1, I will never get the result 2 because it's orthogonal to it. Right? 0 is orthogonal to 1, so I will never get this one. This state, this is orthogonal to this state, so I will never get this result if that state was sent. Okay? And in some cases, I will get 3. Okay? So this measurement helps me distinguish perfectly between 0 and 0 plus 1, okay? Except for the cases where I get E3, where I can't really say much. Okay? So this is just an example. This is just a very simple example of a POVM. It's not a projective measurement, okay? Because the operators are not orthogonal to each other. It's helpful in this weird concutted, situation of Aviad and Elad, but I guess, being black squares on a screen, I don't know how strange they are. And it just, just to give the simple example. Okay. So the last comment that I wanted to make about measurements before we take a break regards realistic measurements and continuous measurements. So I talked a little bit about realistic measurements and the fact that real measurements, in reality we don't have projections. We showed the projection and told, okay, this is a general measurement, but we all stayed with operators and these mathematical constructs. But if you think what happens in the real world there's never a projection. Okay? In the real world you can never have a projection. Why? Anyone? I alluded to that beforehand. Why do we not have a projection? Why can you not instantaneously project a state? All right, I'll give you a clue. Nothing comes for free. What do you need to pay? In physics, what do you pay with? Energy. Energy? Okay. If I collapsed a state immediately, instantaneously, in 0 time, how much energy would I need? Infinite. Okay. So a projective measurement is something that is unphysical. Okay, it really is unphysical. Okay, we can model things with projective measurements, but in reality, in experiment, there is never a projection. It's an idealization that we take into some measurement device that we don't know what's going on inside, and the time dynamics are just too fast for us to understand what's going on, and we say projection. Okay, we draw this photon detector on the board, and we say it clicks if there's a photon, and it doesn't click if there's no photon. But there's some dynamics going on inside that photon detector. And whatever you do, in a real measurement, there is always continuous dynamics. Okay? And there's always continuous measurements. Okay? And you can start taking this apparatus and make it part of your quantum system. Okay? And then treat that quantum mechanically. And then move your classical quantum boundary further out. And you can always expand it further out and out and out. But at the end of the day, however you look at it, your measurement will always be a continuous process. Okay? You can model it as unitaries and projection, but you always have some continuous measurement. And it's in those cases that is also helpful to look at continuous measurements and utilize POVMs. Okay? Any questions about that? If not, take a 10-minute break and then we'll move on to our next chapter.